Hello and welcome back to the stream. So we have our tiny little chip all nice and soldered up. So I'll pull it out from under here and show you on the big screen. This little guy here. So got the microcontroller, the capacitors, and the little leads coming off of it. So next order of business I would like to do is I'm going to get these guys. So a little segment display, and it's got these through hole leads on them. They're super old because they've been in a bag, kind of in an climate uncontrolled sort of environment for, I don't know, probably a decade or more. So I don't know what kind of condition they're in. So what I'm gonna do is pull up the old data sheet for it again. Oops. And connect some wires to it and see if we can just sort of get the get these things blinking. So testing them just with sort of a power supply, like a bench power supply type thing, and then attaching them to the leads that we just soldered on. So I guess without further ado, so I'll go ahead and put this back on the microscope. Zoom out of here a little bit. Got this really nice zoom lens on here. So there you can kind of see, some of these pins. And what's kind of cool about it is, like, so these are, they're LEDs or whatever, but you can see it's sort of like they built up this like complex, like almost like, circuit board type thing, and then all they did is sort of like just they potted it here with this like red goop underneath there. So it's basically its own little like circuit board module essentially, hiding these little LEDs underneath. So basically the only thing that I'm going to do here is we're going to talk a little bit more about flux and stuff, but the flux is going to help kind of take some of the old gunk off of there. Just kind of do something like that, a little bit on there, and then I'm just going to attach some leads to it. Actually, that might be a cool idea. So I talked about wire wrap wire earlier, and we have a lot of it. It's this like ultra fine, like 30 gauge wire, and it's meant to be wrapped around leads to sort of connect components together. And what you can do, and I don't even know if it's possible to see this. You need the microscope for it, but there's like a center hole there, a hole in the center, and then a tiny little hole at the top. And the tiny little hole at the top is what you thread this 30 gauge wire into, and then it goes into this little channel kind of on the side here. You can see a little shiny there, and then you take that, and then the large hole in the center, that is what goes around the lead that you're trying to wrap around. And then you twist this little doohickey. And voila. You can see here, there's now a very tightly wound wire around this lead. And so what I'm going to do is with this flux, I am going to also attach I'm going to put a little bit of solder on there, so that way we have it like, it's wire wrapped, so it's like nice and mechanically secure, and also electrically secure, but just for extra fun, going to add the extra solder to sort of guarantee that it's got a really nice mechanical connection on there. and electrical. So you see that sort of tinning the ends here, and kind of smack it away, get a little excess off, and then you want to try to you want to heat up the wire, the lead, and the solder at the same time with the iron. It's kind of like perfect trifecta thing. Everything to just kind of flow over it. Boom. Yeah, hit it with a little extra heat. Blah. Smoky. And a lot of people say, they're like, oh yeah, you know, it's like all the lead fumes and stuff. There's actually very little lead in those fumes. That is all from like burning flux. You're really only going to get like atomized lead if you are doing something, if you're cooking it with like, you know, fucking 800, 900, 1,000 degrees, just like way hotter than you need to melt solder. So if you have it at reasonable like soldering temperatures, you should be totally fine. You obviously don't want to like huff flux fumes. You know, it's still a lung irritant and all that kind of stuff, and you know, I don't know, in everything in moderation. But also have very nice. I don't know if this is gonna really hurt the audio or what, but I would rather hurt the audio than hurt my lungs. So I got a little fan here, so I'll focus that over here. This setup. So this fan, I'm gonna move it a little bit closer. And I talked about this yesterday. I have this exact same one in my home lab, and all it does is sucks the fumes in. It's got a little bit of a filter here on the front that kind of like, you know, catches and, you know, filters that flux smoke, and it also redirects it. So it just sort of like, it gets the smoke out of your face, which is really nice. So I'm going to move some of this stuff around here, do a little bit of juggling, and get some of these other tools out of the way, out of my workspace. And that way, I can get this guy a little bit closer. So, again, sorry if that, if it makes it hard to hear or it's super distracting, but it's doing good things. So, all right. So in that case, I'm gonna continue with this wire wrapping, and I will go ahead and do the next one, feeding the wire wrap wire to that teeny tiny little hole there. Sticking the lead of the 7-segment display into the center pin of that wire wrapping tool, and then twisting it until it comes off. So I'm using the tweezers here to woo. Bending this around, just kind of secure it, you know. I don't know. So there's a really, like, I don't know, I guess with a lot of things, there's sort of like the spirit of it, you know. It's sort of like, yeah, you want to get a working thing, and or I guess the letter of it, the spirit in the letter, something. No, so you want to get something that works electrically and works mechanically, and you know, of course, behaves like you expect it to and design it to. But one of the nice things that I like about soldering is there's also sort of like, you know, there's a style element to it, and it's sort of like there's things that are like good electrical joints and bad electrical joints, and pretty and unpretty, and like you can spend a lot of time, like many years, sort of like honing the like essence of making like a pretty solder joint. and it takes a really good technician to sort of like get the hang of this over the years. So and that's something that like it's easy enough to do, but you just gotta practice it. It just takes a little while to get the finesse. Oh, and I am looking at the chat. If anybody else hops on, who knows? I got two viewers, so I'm going to hold on 1 second. I'm going to copy this link. I'm going to send it to some of my friends because my friends are nerds and they watch this kind of stuff too. So let me go on Discord real quick. Boop, boop, boop. Not displays. Discord. So this is all made more challenging than it needs to be, or I don't know. It's a lifestyle choice, but I run Linux for most things. I'm running this on Arch Linux, and the ethos of Arch Linux is sort of like, oh yeah, like you teach yourself all the things that you need to know, and there's a nice wiki and supportive community and all this kind of stuff, but it also is sometimes really tricky, and if you want something to just work out of the box, well, unfortunately, that is not in the sort of like, I don't know, it's not in the cards for you. So Arch Linux is focused very strongly on you figure things out on your own. You start from very little and kind of build up the system that you have taught yourself how to build, which means like especially things like audio drivers or in particular Bluetooth. The stuff that I've been dealing with is like you're trying to figure out Bluetooth connections and all that, and there's like 1,000 different ways to accomplish the same thing. Many of them are mutually exclusive, and it just sort of, I don't know, makes for a quagmire of quagmire of configuration. So, but I digress. Pasting this link into Discord, and there we go. All right. Well, I'm going to put this back on just the main screen because I'm not really working under the microscope right now. Maybe focus down here more. So, just chugging along with this wire wrap. So, threading that. And then, whenever I do wire wrap, I'll sort of like, I'll bend the lead once it's in the channel, kind of out of the way. And then slide it over what it is that I'm trying to wire wrap. And then twist. And then there you go. That's like the first row. So they're at least wire wrapped. I'm going to attach solder to these last 3 joints here. Cleaning up the wires, get them nice, get them kind of out of the way here. I don't know. I probably don't need to wire wrap these things. It's just kind of nice and relaxing to try, I guess. Put some flux on here. I need to attach resistors to these things. So I could have just attached the bare resistor leads to it. But I don't know. This is a reasonable strategy to get these things connected together. A lot of this is sort of like, I don't know, it's just prototyping, and there's a million ways to prototype stuff. important thing. Oh no! All right. So this wire, you can see it's got a little dangly bit here, and what I could do is try to wrap it around with tweezers. But the nice thing about it is I don't have to. I'm just gonna cut it off. Just trim that off, and just assume I have enough mechanical connection there to make the other stuff work. So there's what, 5 more leads on this thing, so stand by. But I remember when I was in college, they had us do some wire wrapping, and I was just like, I was so flabbergasted. I was like, oh man, that's so old. I know how to solder. I thought I was so big and bad because I learned how to solder when I was in high school, and like, as it turns out, that's not really, like, I don't know, really anything to brag about. But I wanted to show off my soldering skills to my professors and my TAs, and they're like, that's cool. But we did a lot of wire wrapping because we had these big development boards. So it'd have a microprocessor with a whole bunch of pins and IOs and stuff. And then our labs would be based around you got some arbitrary module, like you got a keypad or something like that. You add this keypad to your dev board, and then you have to whatever, interface to it for so many points or percent of your grade. Two more to go, but yeah. So Ted and Laz, they went home, so it's just me here in the Ologic office, just kind of hacking away on stuff. But it's nice and peaceful. Got a little happy little circuits going, and yeah. The calm before the Monday craziness catches up. So what I'd like to do is try to finish up as much of this stuff as I can, because I have to make sure that it is all cleaned up and definitely out of the way for Rochelle tomorrow when she actually goes and hacks on this sort of stuff, for her day job. Alright, last wire wrap. Yeah, I suppose these wire wraps could be prettier, but I don't know. Perfect is the enemy of good. Good's the enemy of getting anything done. So, I'll zoom back over here and go through the process of... Ooh. Cool. Process of soldering this up. So, I'm trying to find something to clean the tip with. So we have these things. This is kind of cool. So it's essentially like Brillo, but it's, I don't know, some sort of steel wool type thing, copper wool. But much like the desoldering wick, there's a lot of surface area, and the solder has a high affinity for it, so you put this thing in, kind of move it around, whatever, and it scrubs the tip clean. Because old solder and stuff, it as it collects on the tip, it'll oxidize and just makes it hard to create really nice joints. So I put a little blob on the end there, and then let's go ahead and do this. So I'm finding more and more that this microscope is very much it's more for your benefit than it is mine. I'm looking at this thing just with my own eyes, which, I'm very thankful that my eyes are good enough to do this. I wear contacts, but I have learned from a lot of the folks in the office past their 40s that, like, yeah, the ability to look at that kind of stuff, that sort of accuracy, goes away really fast. You don't realize it till it's gone. Whoops. Got a big old solder bridge in there. A lot of these through-hole components, the strategy for getting rid of extra solder is to use a solder sucker or like a desoldering pump. I'm just gonna hope I can get by with a soldering wick here, and just end up going through, because the through-hole components, they just use a lot more solder, and the desoldering wick is nice for relatively small amounts of solder that you're trying to get rid of, but oftentimes it just saturates the braid. You need to remove huge chunks to use the pump. I'm having trouble, one, keeping this in frame. You know what I would like to do? I would like to find, I wish I had some double-sided tape. I think I might just take some of this Kapton from earlier, and then just fold it over on itself. And that way, yeah, I can just keep this thing in place while I do my soldering. Gosh dang it. Ugh, fingernails. Alright. So that is good enough for now, I think. I hope. Get a nice view of that big, fat bridge between 3 pins, not just 2. Get my desoldering braid, and then try to heat everything up at the same time. That's sort of like that's the name of the game here. I don't know if you saw, I got some of that flux syringe. I was able to put some extra flux on it. Now we have a bridge only between 2 pins, and I'm hoping that I can just slide this in between there and get that to work. Alright, cool. So, we can see now we've got no more solder bridges. I think that one at the end there still needs some solder to hold it in place. Also these guys in the upper right here. I'm going overboard with the solder and the flux and the wire wrap and all that kind of stuff, because I want to make sure that we get really good connection to these pins in here. I'm dubious as to whether they're, like, I don't know, super corroded or have like a layer of oxide on them and stuff. It just makes them hard to work with. So yeah, I think that's pretty good. Let me go ahead now, turn that fan off, quiet things down a bit. I'm going to go back to my screen capture here, and then let me So opening up a new page here. I can figure out what the heck I'm doing. There it is. All right, and then finding this particular data sheet. I don't know why I don't just save these PDFs on my hard drive. Ooh, actually, looking at this guy. So I was looking at this guy, and it looks like it is kind of experiencing some of the things that I was worried about, where it's like it's got that oxide layer and just doesn't have really good adhesion. You can see it's kind of like it didn't do a nice job of flowing evenly over the pins. It just sort of blobbed up on the wire wrap wire lead. So what I'm going to do is just sort of like hit it with a little bit more flux, a little bit more love, and a little bit more solder. And hopefully get a nice solid connection on there. That should be good. Man, these close-up shots of my fingernails are soberingly disgusting. It makes you think about fingernails. Yeah, I really think that is going to be good enough. So let's call that reasonably attached for now. And then we can go ahead and start connecting these things up, as long as we can find this part again. So this guy here, as you can see, it says DL 760R. So this is the part number. So we're looking for basically any sort of 7-segment display that says 7760 in it, and that means it's probably going to be pin for pin compatible and have some other variant to it, or some other, it'll be either a manufacturer. I think this DL is sort of like a manufacturer prefix or something like that, or maybe it's this F. I have no idea what this 8223 is. A lot of times this will refer to like a date code. If you're trying to identify the batch, maybe this was made in 1982 in the 33rd week. So it's like, what was the 33rd week? That puts it a little bit after halfway through the year. So September-ish. September of 1982, these parts were made. Maybe. So so let's see, 7760, 7760, seven segment display. Dang. Let's embiggen this. 7-segment display. I mean, that's what is this? This is DL 7760R. Datasheet maybe. Come up with something else. Alldatasheets.com. Yeah. This is a bummer because it's so freaking hard to find these things, man. 7760R display. What the heck? Okay, I found this once and I built a board around it, so I'm just going to assume that my pinout here is correct. So there we go. This is the pinout. And something that we can check, which is kind of cool, is on this guy here. So there's two ground pins, right? So there's pin 3 and pin 14. So what I can do is use my handy dandy beepometer, or my multimeter, and set it to the beepometry setting so that if you're testing continuity, it beeps at you. So what I would do here then is say like, okay, what I understand to be like pin 14 is going to be, let's see, pin 14 is going to be this guy here in the well, bottom right in this case, but oh, you can see a little solder blob, little tiny solder ball. Oh, and these things will get you though. Like these guys here, you can see like right there, that guy. Tiniest little thing. But these things, like they're microscopic. They're really, really difficult to catch. But like those are the things that'll like cause shorts. Like they'll sit between two pins in a package or something like that after reflow and cause all sorts of problems. So that's generally why you clean your boards after you're done soldering. So it goes between what does it say, pin 3 and pin 14 on this thing. So I'll turn this around. Right. This is what, 4 pins in a row. So that's what D, DP, CG, a space, something, and then ground. This is now in the upper left. Turn this part around, and then it's also this 3rd pin here. Haha! I'm getting that. Cool. So, that doesn't show that the pinout is entirely correct, but at least it shows that the ground. There are 2 pins at 14 and 3 that seem to be connected internally somehow, and I would like to think that the piece of paper that I found when designing the circuit, that those are the correct pinouts for it. So what I will do is then say I guess we can do A, B, and C. Wait, we got 4 wires, don't we? So there's 4 wires. Let me find some through-hole resistors, I think. Just because I want to use the leads on them. And let's see. You can do calculations on like how much current you want. Generally speaking, for most just kind of jelly bean run-of-the-mill LEDs, it's about like, I don't know, 20 to 30 milliamps of current. And then the way that you calculate it is because like in order to make an LED turn on, you have a voltage drop across it. And that voltage is often fixed for a particular type of for specific colors. So different colors have different voltage drops across them, and that's just because of the physics of the actual like semiconductors inside of the LEDs. The way that those things work is like a diode is a PN junction, which means you have like a chunk of silicon that is doped. So it's sort of like it's finely controlled contaminants, and these finely controlled contaminants will sort of like they will provide extra. They call them well. There's extra electrons. So there's an abundance of electrons in this this lattice structure that all the silicon creates, and the that is then called an N-type semiconductor. It's doped N-type, and you can then add another sort of contaminant to it. I think it's like boron. I forget what makes it N. What contaminant makes it N-type, or what material? But you can also provide an abundance of, like, they call them holes. You can do math on them where like you can treat them as particles, but really what they are is like it's an absence of an electron. So it's just like it's a space where an electron can go into. But you can treat them like actual positively charged particles interacting with negatively charged electrons. So it's kind of like weird to wrap your mind around. But when you have this p-n junction, it's just these two things butt up against each other, and they have certain properties as they interact with each other that create, this junction, and that when you apply voltage in a certain way to it, you create your light emitting diodes, and it's a little hand wavy, and I'm a little rusty on my math and stuff, so forgive me for that, but. Basically, the color is determined by the sort of like the band gap. So it's sort of you have electrons that once you excite them, they jump to like an orbital, and then when they come back down, they release a photon. So they're sort of like they get energy, they get excited, they go to this higher like orbital state, and then they come back down and release a photon, and like that energy transition corresponds to, as far as I understand, a release in light of a particular frequency. So all of that to say, red LEDs have a lower voltage drop than blue or green. Generally speaking, you're going to have like 1.2 volts or something like that for red LEDs, sometimes less. For a lot of like diodes, it's like 0.7 volts. For blue and green, sometimes it'll be as high as like 3 volts or 3.3 volts. So you have to have at least that much voltage on the anode side of the LED just to like push an electron to that like higher orbital state to produce that color. I don't know. I should probably like make a video or something that explains that better, and I should learn that better myself so I can explain that more properly. But in the case of this thing, just sort of rules of thumb. If you have 1.5 volts forward voltage drop, the power supply is 3.3 volts. You want about 25 milliamps of current going through these things. So, I don't know. You can sort of, within the range of like, a couple hundred to a couple kiloohms is an appropriate value for a resistor. And you'd still be able to like, see the LEDs light up pretty well. So, I think I'm going to go with, just because these are pretty small, they look like they're nice and easy to work with. These are 330 ohms. So, I don't know. I forgot my resistor color codes, but these things correspond to, like, the colors correspond to numbers, and I don't know. It's sort of like, I don't know. I kind of liken it to when they used to have you, like, you were forced to learn Morse code to get your ham radio license. Now it's like, it's nice to know and really useful for ham radio stuff, but it's not a requirement. Same thing for like resistors, because like almost nobody in the industry uses through-hole resistors anymore for like production stuff. Uh, there's not a whole lot of reason to like know and understand what the colors correspond to and all that. But you know, it's also helpful to just kind of know if you're working on them for some project. Excuse me a sec. Let me check my phone. All right, so now what I'm going to do here, because we have these 4 wires that we soldered on earlier, I would like to add a blob of hot glue. Let me check these one more time. I think this is all fine. I'm a little wary about that one on the bottom right, kind of like second up. It seems a little dubious. Again, kind of focusing more than I should on it. But cool. Well, I removed the wire and also created a solder bridge. This is why I should just learn to leave things alone. All right. Okay, cool. Use the solder bridge, get rid of the extra solder there. And then line that up as best I can. I want to hope that the residual flux around here that I have yet to clean off will allow me to tack this down. See, that is nice and secure, I think. Alright, gonna use the beepometer. And as far as I can tell, those are separate. Okay, cool. Well, good enough, I suppose. Yeah, so something that would be cool to see. So a lot of times the white lettering, it's called silk screen, because oftentimes, or at least in the past, they used to use silk screens to apply it. But in modern days, it's like inkjet for the most part, and it's neat to see. Sometimes for like really small features, you can tell if it's inkjet or silk. I think in this case it's inkjet, because if you look at the eye, you can see, point at it. So it looks kind of like there's like 5 dots, you know, because it looks kind of like a compass rose there. So it's sort of like 1, 2, 3 vertically, and then 1, 2, 3 horizontally, you know, that like overlap in that middle part there. So I don't know. I would probably guess that this is silk, or sorry, inkjet. And you'll find that like a lot of times for small runs, they'll use inkjet because it's you don't have to have any tooling and all that kind of stuff. But if you're doing huge things, huge runs of like 10,000 boards or whatever, it actually is cheaper to get a silk screen made, so you can just like whip up, you know, just build a jig and just do thousands of these things. So I just was heating up the hot glue gun. As you can see here, just a blob of hot glue, and we will let that cool. And assume that will do what we needed to do for the time being. And that way we get a little bit of strain relief and so on. So that can always be fixed later. We'll just give it our best shot for now. All right, so with those leads coming off, those are all going to be anode wires. And what I need to do here, is connect wires between the anodes and cathodes. And what I'm doing here is actually, like, rather than using the shift register that I designed into the board, I'm just connecting the LEDs with their resistors directly to the GPIO pins on the microcontroller. And I'm doing that in order to test this particular setup. And what I plan on doing once I kind of verify that this board allows me to program the microcontrollers and so on, is I'll probably set it up. I'll probably redesign this board actually to be smaller. And then from that, you know, build something that lets these devices interface with each other a little bit better. So all I'm doing is just wrapping this resistor lead. I picked an arbitrary pin, which is probably a dumb idea because this is probably pin 14, isn't it? Wait, no. Okay, so this is A. That's good. A. And, well, because we only have 4 pins, nah, I'll leave them attached. I wasn't going to cut them, but we can test all the LEDs separately. So that, wrap in 1, and then I guess I'll do F as well. Yeah. So, been talking a lot with Laz, who you saw in the back there, and I don't know, he's an interesting guy. He's another Florida refugee. I don't know, I find that, like, you know, I'm here in the Bay Area in California, and I find that, like, a lot of people that I end up spending my time with are sort of like Florida expats, that have a surprising number of them have, without any sort of, like, you know, plan or sense of security or anything like that, they just sort of like pulled the ripcord and like made their way west with like hopes of figuring it out. And like, I don't know, I was in that boat. My friend Ted was in that boat, Anthony, Laz, you know, a whole bunch of my friends, and they, like, I don't know, it's been tricky, and we've all had our kind of, like, I don't know, weird you know, particular struggles and so on, but I'm amazed at just sort of, like, I don't know, I guess the it seems like a statistical anomaly to meet so many people from the same part of the country doing the same thing and kind of ending up in the same spot. So, I don't know, just kind of cool. So I was looking here at the pinout that I made, and I think this is pin 6. I think that's a no connect because I marked it as a no connect on my board, and yeah, I don't think it does anything. So I'm not going to cut the lead on the part just yet because I might need to solder something to it in case I am woefully wrong. But yeah, for now we'll just let it ride. I think what I also would like to do here is I'm a little trigger happy with my hot glue gun, so I'm gonna add some more hot glue to this. More potting material. Oh yeah, just freaking slathering it on there. Whoa. That's right. I think it's a little late in the day, so I'm just sort of, I don't know, a little more out of it. Had my dinner, now I'm getting tired. So I'm just making a mess mostly. But that'll do for now. Wow, look at all that. Oh god. Ah, frick. Ouch. Well, a nice little trick if you need to cool down hot glue in a hurry. This stuff here, this canned air, there's some sort of refrigerant inside of it, so it's meant to like, I don't know, have high expansion of something, vapor pressure. But if you turn it upside down and you get the actual liquid that comes out of it, it's really cold. And it evaporates really quick. So I spray that on hot glue sometimes, and then it'll evaporate. Sometimes you can even use it the right way up, and you blow off some of that froth that accumulates there. And that way, if it needs to like set real quickly or something like that, yeah, you don't have to babysit it or risk your fingers getting in the way. So it's nice, I guess. All right, so this one is A, F, ground, E, and those letters correspond to the different segments. Alright. Just kind of doing my thing here. Yeah, when I was, I don't know. I found, like, a lot of the stuff that I do is, like, I really enjoy the, like, I don't know. What do you call it? Like, technician style work. So, even though I do a lot of like design engineering, for my day job and stuff, I find that, more so than designing stuff in my free time, I really like soldering in my free time. And it's sort of like, if I walked a different path in life, it's like I could very easily imagine myself being a solder technician, or I don't know, like, I don't know, doing something like that. Some sort of blue collar type work, which is, it's nice. It's nice and satisfying, and like, I don't know, it feels much more tangible than a lot of like design engineering type stuff. So I get a lot out of it. So what I think I might do, we got 3 resistors here, so that's 3 IOs. Got 1 more IO that I can break out. So what do we call it? 14 is ground. So I'll tie that together with this other ground just to sort of let it be known. And by ground, that just means the cathode. So if you have a some sort of a driver for these things, you just connect it, to the cathode spot instead of the ground spot. And in this case, it's the negative, like low side of the LED. And the way that I always remember it is like, I don't know. I have a cat named MOSFET, and he's a super sweet cat. But like, I don't know. I always like make the mnemonic in my head where it's like, you understand like the difference between anode and cathode because cats are, they're aloof. Cats are bad. Cats are negative. And like, because a cat is negative, the cathode is the negative side of the LED. I don't know. That's that's at least what always comes to my mind. It's not true, but it's memorable. So I don't know. That's one strategy. Everyone's got their own mnemonics. Whatever helps you remember. Yes. Circuits. How do they work? Magnets. Probably. It is true. So, I was talking with some coworkers about this, and it's like, so you got Magneto from X-Men, right? And Magneto, it's like, Magneto's got the power of magnets, right? So it's like he can only make things. So metals, there's only 3 types of metals that like can become magnetized, which is your iron, your nickel, and your cobalt. So it's like, so steel is just like a heavy iron content and all that kind of stuff. And it's sort of like there's that scene where Magneto lifts up Wolverine and is like bending his like claws and stuff like that. And it's like, well, that means then that adamantium, what's his face is like Wolverine's skeletal structure or whatever, it must contain either high amounts of like iron, nickel, or cobalt. And it's like, can Magneto control anything that doesn't have those metals in it? Who knows? And okay, let's say that he can do stuff with magnetism. Can Magneto like use his magnet powers to like, I don't know, move a magnet inside of a coil and generate electricity? So does he have power over electricity as well? Because I feel like, this dude basically create like a, really crazy freaking awesome energy source with his mind just by thinking about it. So just to keep these things out of the way here, so I got 4 resistors attached. The grounds are connected together here. And then I've got these 4 extra wires for the 3 remaining segments and the decimal place. So what I'm going to do, just because I don't want them like interfering right now, if I need them later, I'm going to strip the insulation off and then attach them to whatever. But for now, I'm just gonna snip them. So there we go. This is our experimental setup. So what we will do now is attach these wires arbitrarily. And right now I'm just twisting these wires, twisting the leads together, and then I'm gonna touch them up with solder. I don't know, maybe if I focus the camera right in my belly. No, that's gross. I'll just hold this up to the camera and we can look at my smiling face instead. So wrapping these around, and then once all of them are wrapped, then I'm just gonna hit them with a little bit of solder. These guys are gonna be nice and easy because they're, you know, they're not oxidized, not corroded or anything like that. So they'll be super easy to solder to without any problems. Knock on wood. Maybe if I did a better job of wrapping them, it wouldn't be so hard. So yeah, essentially you have like a piece, you have like the pad on the board, then going to a resistor, which is then going to the LED. And all that is to, I don't know if I mentioned this or if it needs clarifying for the folks watching, but the resistors, they, you know, are essentially like check valves for electrons. And, you know, if you're trying to control your current to a specific value, then you do it with resistors or some other, you know, more advanced techniques. But this allows you to very simply and very cheaply, importantly there, control the current in a circuit. So we're assuming that the input voltage on this thing is going to be 3.3 volts, which I gotta double check because some part of this circuit is it runs off 1.8 volts. It's sort of like the internal voltage, and then the external like I/O voltage, VDD I/O, that will run off of 3.3. So it's kind of funny because it's like, I don't know, it used to be that like, oh yeah, all circuits they ran off of 5 volts and stuff, but as chips got faster and faster and like the processes got smaller and smaller, all these like sort of internal voltages are shrinking. So like a lot of the times if you're dealing with electronic circuits, especially complex things like processors and like FPGAs, field programmable gate arrays, or like, you know, anything like that, a lot of the time they'll have like, they operate off of like, you know, 1.0 volts, you know, 1 volt or 1.8, 1.2. Some of them are even like as low as like 0.3. So if you have like 0.3 volts for your power supply, it means that like your power supply has to be incredibly low noise, because it's like, okay, it can tolerate maybe like, I don't know, like 10% over your like specified value, but any more than that is it like blows up the chip. So it's sort of like you can handle, I don't know, for your 0.3 volt power supply, you can handle, you know, 0.35, and then the chip breaks. So you have to have like all these bypass capacitors, you have to have like a really stable input voltage and all that kind of stuff. And like, I don't know, it's made like electronics much more power efficient, and that's how you get those like super low power cell phone chips and all that kind of stuff. But it's also kind of hard to design for, and like, you know, well, I guess maybe not hard to design for, but at least more stuff that you need to be aware of when you're designing. And all right, what I will do, I don't need the microscope for this. We're just gonna have to tolerate my belly for a little bit. Rather than shine that in there, I don't need that. I think what I can just do is shine this here. So all I'm really doing is these wires that were twisted together, I'm just putting a little bit of solder on there. No major tricks or anything like that. Not even really paying attention too much to the stuff that gets soldered. Oh god, fuck. Well, as long as I can keep it on the little plate here. So, ugh, smoky. All right, I'm gonna turn the fan back on. Kind of get it out of my eyes and face here. So, I guess to kind of go back and reflect on why the heck I'm doing this in the first place. So I'm part of an organization that I started with some friends called Cluster Fights, and the way Cluster Fights works is, it's a group of, like, I don't know, computer architecture enthusiasts, which I guess, I don't know, only in the Bay Area, I guess. Maybe some other places, but, like, I don't know. We're nerds who like hacking on computers and computer architecture and all that good stuff. And we build supercomputers. And the trick is, like, okay, you can buy a laptop for whatever, $1,000, but can you get, okay, so you say, all right, $1,000, and then it's like $1,000 for a 3 gigahertz processor. All right, so it's like, that's like $300 for $300 for, like, per gigahertz, right? But what if you have, like, a bunch of Raspberry Pis that are, like, whatever, one and a half gigahertz, and those are $35, and then it's like, all right, cool, like, for $300, you can get 10 Raspberry Pis, and it's like, is it possible to build computing systems that are, I don't know, that are more powerful and more cheap, but they just use cheaper components, use different computer architectures, use, high parallelism instead of, like, the single core stuff that a lot of our, modern computer architecture uses. So it's just an opportunity to play around with, different architectures and parallelism and clusters and all this sort of stuff. And that's what this microcontroller board is for. It's sort of like, it's got a Cortex M0, which is an ARM processor in it. And you can buy so many of them for so cheap. And it's like, what sort of, like, cool computations can you do with them with a really cheap, really powerful cluster of small computers? So that's kind of what this is about. So the SWK says that's one heck of a filter section on that switch mode PSU. Which PSU are you talking about? Sorry, I kind of missed that. Kind of rambling. But oh yeah, so talking about the probably the ultra low voltage stuff. Yeah, generally with the 0.3 volt, like ultra low power type power supplies. Normally those things will be those are linear regulators for them. Yeah. So you'll have you'll take your switch mode power supplies and you'll build up a switch mode power supply that, like, basically brings your input voltage, which will be like 5 volts or 3.3 volts or something, and then your buck regulator will then bring that down to 1 volt, and then from that, like, you'll have for your very, very low voltages, you'll have your linear power supplies. And at those sort of stages, they're generally because, like, linear power supplies they're less efficient than switch mode power supplies, but they're also lower noise. And what the SWK is referring to there is, like, you have output ripple that you have to worry about a lot more with switch mode power supplies, and that can be problematic, especially if you have really, really tight noise requirements, ripple requirements. So what I'm doing now is I'm just going to grab some electrical tape or some capped on tape, depending on where I can find it, and basically just wrap it around the resistors so that I can protect them a little bit. I got this capped on tape. What I think I'll do is just cut a couple of strips of it with this box cutter, and then that should suffice. For now, anyway. And that'll just keep things from accidentally shorting against each other. So in an ideal world, this would be heat shrink, but get by with what we have. That's why the military used 400 hertz for the longest time, because less ripple than 600 hertz once rectified. Huh, that's really interesting. I didn't know that. I guess too, like the higher the frequency, I guess the easier it is to filter. I think, because that's why like I guess with your switch mode power supplies, like the higher the frequency, yeah, the less ripple you get on the output, and I guess the easier it is to filter. So that's really cool. I never knew that the military used 400 hertz for that. Was that sort of like they had like their own internal? This is for like their own power generation. Like their own power generation was 400 hertz, or like what was it that was entering into the system at 400 hertz there? This was mainly shipboard the Navy. Okay, interesting. And do you know if that, like, are most Navy ships, well, I guess probably not most, but is that being made by, like, diesel generator? I was reading about something that, hey, so this came up, it came up on Reddit somewhere, but they were talking about it was like an old paper from Skunks Works, which is like that's the high research and development branch of Lockheed Martin, doing all sorts of like crazy special secret projects for the government, building all sorts of crazy planes. Let's see, depends on the boat. That's dying out due to the COTS program, commercial off the shelf. Yeah. So so it's like it's much nicer to have like commercial off the shelf stuff, and even though it like I guess it's less reliable than military things. It will like my understanding is like they're changing from ultra high reliability stuff to easier to replace things, so that you can buy cheap off the shelf things, upgrade them more easily, and sort of like I don't know, kind of move a little more swiftly on stuff. So that's cool. But this Skunks Works thing that I was reading about, they were talking about like what is theoretically the largest airplane that you could build, based on like 1960s technology, and it's like, well, okay, the largest plane that you could build is this like it's an aircraft carrier in the sky. So it's a flying aircraft carrier, and they talked about like, okay, it's gonna have to use like 8 turbine engines or something like that, and the way that you like power it is it uses a nuclear generator. So there's gonna be a nuclear powered flying aircraft carrier, and this thing would it would superheat this like radioactive like slurry, this like radioactive salt, like uranium salt, and they would pump that through basically the body of this aircraft, and they would have heat exchangers because they wanted to heat up the water without making the water radioactive. So they would have these heat exchangers heat up the water, and then that water would turn to steam and then turn the turbines that propelled the aircraft. And like this crazy monstrosity was designed to fly for like 6 or 8 months at a time, something crazy like that. And it was also designed so that it could fly at full speed into a granite mountain and not have any like radiation leaks or anything like that. And it was just like, I don't know, I'm positive that it ended up just being like too expensive and too impractical to build, but just as sort of an exercise in like, I don't know, pure research. It was super interesting. Kind of wish they did make something like that, but it feels very very much like that device, or not device, but that machine from the Avengers, that like big flying thing in the sky, aircraft carrier in the sky. So what did he said? Oh, Bob at DPI. 600 hertz was used on airplanes in particular. Inductors were much lighter. That makes a lot of sense. Yeah, because you can have higher switching frequencies, or with higher switching frequencies, you can have smaller inductors. Yeah, so that's nice. Less switching losses. And then they build Fred. Fred instead, aka the C5 Galaxy. Yeah. Yeah. I just like there's Moffett Field here in the Bay Area, and like sometimes you'll see these like, you know, I don't know. Honestly I don't know how to recognize a C5 Galaxy from the air, but like we see these like gigantic cargo planes, and they will like, you know, fly and do their like, I don't know, their low altitude approaches and all this kind of stuff, and it's like, oh my gosh, like something that big really doesn't feel like it should be flying that low, and just cruising around doing its patterns. But yeah, I don't know, those things are super impressive. They're like really awesome feats of engineering, and like, you know, sure, I know like aerospace has a lot of like whatever, it's got its bureaucracy and, you know, kludginess and all that kind of stuff that a lot of people have to put up with and isn't very fun. But there really is some awesome stuff, and like building like high reliability redundant systems and all that kind of stuff on planes and aerospace stuff is like, I don't know, I think it's pretty cool. So right now I am just attaching this ground wire to this pad, but you know, the ground being this crazy heat sink that it is. Oh, there it is. I want to make sure that it sticks properly. Okay. Yeah, because it like pulls out a lot of the heat here. Did I see you actually use liquid flux? Yes. So we have this stuff, this Chip Quick, and it's like, it's super nice. It's tacky, and well, if you get it on your fingers and stuff, it's like sticky and gross, and you got to go wash it off. But it flows really nicely and helps all this. All the soldering is made easier by use of flux. So it's nice to just sort of like have in the toolbox. So this is now, what was that connector that kind of broke off the edge there? I broke out the 2 power pins, the I2C, and then there's a connector just for all the GPIO. Oh, okay. Well, dang it, I didn't even need to solder to the surface mount things. Pay attention. It would definitely help if I paid attention to my circuit that I actually made here. But I guess let me go to the screen here. So what I was looking at is so I soldered wires to this thing here, to what is it, A, F, B, and E. But I could have just ignored this thing entirely. I could have just used these GPIO pins, which is, I'm feeling kind of dumb now for doing that, but because this has a connector, go figure. But that's all right. What I'm gonna do then instead, so this is 3.3 volts, and I put 2 power supplies here and ganged them together so that they could do like load sharing, because it's 250 milliamps, and the chip itself might use more. So I don't know, I could have just picked a part that provided more power, more current, but I was getting lazy and didn't feel like doing too much. So I did, however, break out this here, and what I might be able to do, because I didn't populate the regulators, I might be able to put a connector in here onto J5, and then from J5, I can just like inject power directly into the thing. And that's where I'll attach the lead for the bench power supply. Dude, so many people on Twitch hacking hardware and never break out the flux. Dude, you gotta link me to some of those folks, cause like, so I'm new to this whole thing, but like, I want to find people who are doing hardware hacking and stuff. So if you got any streamers in mind, feel free to post them here. So I'd love to host those guys and check out some of the stuff they're doing. Guys and gals, whoever. So let's see, a little input voltage there for VCC, all those things. All right, so I'm gonna get just a little male header. I want to find just a small 3-pin 100 mil header. Whole container of them. Yeah. So this little guy here, so just a standard run-of-the-mill header. I'm just gonna break off 3 of these pins and then attach it to my board. So I already told Bob this, but when I ordered this board, I happened to be enjoying one or several glasses of whiskey, and when the boards came back, they didn't have any solder mask on the bottom side, and I was upset about it, and I was like, oh yeah, it's a manufacturing problem. And then Bob, he mentioned, he's like, yeah, is it a manufacturing problem or is it a whiskey problem? And I was like, it's probably a whiskey problem. But yeah, because I think when I was building the files, building the manufacturing files, I didn't include the bottom solder mask layer. So they're just like, listen, you probably need it. What we can do is not put it on the bottom on anything, or we can put it across the bottom on everything. And I was like, oh, what about, like, I don't know, doing it just the way that I intended? And they're like, well, you can either resubmit files or we can do it this way. And I was like, well, I don't want to resubmit files. So they just put solder mask over the entire bottom of the PCB. That's okay. I am very, very pleased with like JLC PCB is like how fast they can crank these things out. Because like normally from China, I like, sometimes it'll take weeks or whatever, but with like DHL shipping on these things, like most of them get here within a couple of days. They're surprisingly quick. So, all right. Well, I have this header. I have my LEDs. I have my microcontroller. I think the next step, VDD-IO. I think VDD-IO, I want in this case to be 3.3 volts. So I'm going to short that pin. Make sure I short the right one here. And then I'm going to just attach the lead directly to it. So let me bring this guy down here, show you what I'm looking at. And it is, I think this is J3 here. No, this one here. So you can see this was originally meant to be a jumper, so you could put a jumper between these two things. What I'm going to do is I'm going to clip this lead because I don't need it. I'm not going to do anything with 1.8 volts. And then I'm going to bridge these two guys together, and then I'm going to attach a clip from the power supply to one of these two pins. So that will be how I get power into this thing. Back to my microscope. So this is where we intentionally want a solder bridge. It's amazing how easy it is to do once you're trying to actually make one. And then on the other side here is where I'm gonna clip the lead I don't need. So this guy is the 1.8 volts. Oof. You can see how poorly taken care of these cutters are. Woo! 100 boards leaving off a required pull-up and resistor network. Yikes, man. That's I can relate. I can relate. Yeah. There's definitely been some next level cock-ups where we forget some major component. There have been like times when we've had to sort of like get at least here at Ologic, have to get like all hands on deck and sort of be like, oh, all right, all free hands available. Let's do some manual rework, and everybody's kind of like cranking on soldering irons and stuff. So those are fun times. But yeah, it goes to show that like no matter how long you're doing this, it's like there's still a lot of ways for stuff to just like slip through the cracks. What do you mean that keypad grid doesn't work? Hey man, it works. You just gotta, it's an artisanal circuit, right? So you have to add your own loving touch and your own pull-up resistors to it. So that's what differentiates it from the working ones. Sense of pride and accomplishment over adding your own pull-up resistors. All right, so there's this. I guess I should add a ground pin. I think there's one. Let's see. Oh yeah. For this. Okay, cool. Yeah, pin 14 there. Let me add another one of these guys. It's meant for external pull-up and debounce caps. Nice. So the SWK, are you do you do are you an electrical engineer? Do you do this kind of stuff for your day job? Right, so I'm adding a ground pin on here, and that should be the finishing touch, and then we can do the smoke test. The smoke test is basically just, plugging it into power and setting the current limit really low on the power supply, and when we do that, we'll see if it, at a fairly low voltage, we'll see if it's, current limiting itself. And if it's current limiting itself, then we know that there's a short somewhere, and we probably shouldn't power it up to full, whatever, to circuit blowing current levels. So what I'm gonna do, I'm gonna switch this back to this thing, and then cool, day job is software. In previous life, I was trained component level repair with an engineering bend. Oh, nice. That's pretty awesome. So, yeah. I don't know. I think it's cool that, finding folks come out of the woodwork here, talk about circuit things and, software things and all that kind of stuff. I don't know. I'm trying to learn a little bit more about software but I find that most of my time is consumed with hardware these days. Alright, so let me get this guy out of the way. Let me put this microscope off in the corner. Should be fine. Plug it. Okay. Alright, so I'm going to go off screen for a second, go see if I can wrangle up a power supply, and we can smoke test. See if we can get some code onto this thing. Alright, I will be right back. Please sit tight. All right, so I found a power supply. It's this. It's fairly nice. It's a Rigol DP832 programmable DC power supply. So I think rather than move the power supply over here, I'm gonna try to move the microphone and move my laptop. So I'm gonna have to unplug stuff, maybe. Can I just drag everything over? Who knows? As you can see, I am clearly still trying to figure out this whole frickin' streaming thing. Probably never gonna figure it out. Probably just gonna be it's gonna be like this every single time I stream. Just moving cameras around, doing all sorts of crazy shit. That's okay. Alright. Get that out of the way. And you can see, make sure that there's nothing super secret going on here. I think everything's been covered. That's good. Get that out of the way. But we have this big old beefy behemoth. This guy. And this thing, I'm just going to turn on the power strip first. It's a programmable power supply. I don't know. I think it can do some pretty sophisticated stuff, but in our case, all I want to do is set it up so that it does 3.3 volts. So let's see, 3.3. Okay. And then I'm going to to set a really, really low. So I'm going to go then to the current settings. And then I want to set it to the super low. So I'm going to try to do like, I don't know, 10 milliamps or something like that. 20 milliamps. That should be fine. And then what I'll do is once I power this thing on, it might have like voltage limiting, or sorry, current limiting on it. And when it current limits, it drops the voltage down. And if it is clear that there's no internal shorts or anything like that, I will slowly crank it up until the voltage level is no longer like letting it current limit. So the voltage will get to 3.3 volts, and its current will be, I don't know, potentially something more than 20 milliamps. So let's see that here. And then it's nice we have these little leads. So we'll hook that right in there. And right now the supply is off. And it has a little enable switch. So what also might be fun is if I've somehow done something terribly catastrophically wrong and it blows up, it's always nice to get that on camera. So I don't suspect that'll happen in this case, but you know, you never know. So, wow, okay. It's showing 3.3 volts and 0.00 amps. I suspect this is just a very low power microcontroller, and because there's no code on it, it's not doing anything. There's no internal oscillators running or anything like that. So I got to get code on it, and then we can test it out. But yeah, it passes the smoke test, so that's good. Turn the power supply off, disconnect everything. That was underwhelming, but whatever. That's what you got to do. So, what did the SWK say here? I don't get to hardware hack as much as I like these days, and I'm at a point where I'm going to more management than actual coding. Sometimes I just wish I put the phone on D&D. Debugging, leave me alone. Yeah. I'm still, I don't know, relatively fresh, I guess. I haven't been doing this for too many years. I mean, I started laying out circuit boards. I think this is like probably my first, like, freshman year of college. I was working with this group called Formula SAE, and they built like this like race car, and it's mostly like mechanical aerospace folks. But there was like me and this other guy named named Fred, and Fred Wheely, and we were like the only Sparkies on the crew. But yeah, he kind of like, you know, was the first person to show me Altium and like, you know, show me how to start laying out printed circuit boards and all this kind of stuff. And I think I might have messed around with it a little bit with like Eagle in high school. But as far as like professionally, I think I've been doing boards for like, I don't know, like 4 or 5 years, something like that. So as far as these sort of professions go, that's still pretty fresh. So I still get to hack on a lot of this kind of stuff. But I can understand the desire to, like, you know, yeah, just kind of go back and get your fingernails dirty type things. So sorry, let me check these messages real quick. So my dad and my stepmom are coming out to the Bay Area for just to kind of hang out. They're doing like this, what is it? This kind of like Starlight tour or something like that, where they're starting in Seattle, and then they're taking the Amtrak overnight down to San Jose. And I'm just trying to coordinate with them and figure out what we're doing here. So sorry, time's a little bit of the essence with that. Okay. Cool. right, so what I think I'm gonna do, I'm gonna go to the screen grab here. At this point, this is something I don't know if I'm gonna figure it all out tonight, but I have this development board, and this development board has the same chip on this little board that I made, same microcontroller, as well as another Cypress part that's like this larger chip. So this tiny guy over here is my microcontroller, and this guy here is the programmer for it. So what I need to figure out is how I can get this particular like development board, how I can jumper the programming wires out of it. So instead of programming the microcontroller on here, it's instead programming the microcontroller on my board. And on top of that, I need to figure out the dev tools for these Cypress parts, because the issue is like, so I'm running Linux on this computer, and I have no idea how well I'll be able to get the Cypress tools running, because like their IDE and all of their like proprietary, you know, what do they call it? Their programmable system on chip, like, you know, intellectual property things. I don't know how well that's going to work on Linux. I don't think it's ever been. I don't think they ever anticipated, or like I don't think they support that. So what I've seen, if I can bring another window up here. All right, I'm gonna do some Googling and then kind of talk my way through it. But this might not be as interesting. It might even be less interesting than watching somebody solder a circuit board. So, just watching someone Google things. But what is kind of cool is this thing has it has FRAM on it, which is like what, ferroelectric RAM. What's the principle of operation of that stuff? Is it ferroelectric fluid? What is this stuff? Random access memory, similar to DRAM. Huh. Non-volatile RAM offers the same functionality as flash memory. Faster write performance than flash memory, lower power usage, and a much greater maximum read-write endurance. Wow, that's really cool. Data retention more than 10 years. 10 years at 65C, up to many decades at lower temperatures. Holy cow, that's really interesting. Market disadvantages are that it's lower storage densities. Interesting. I am just amazed at like all the different like ways we have figured out how to like store information in electronics. I found this this computer file. Video computer file. What was it? They were talking about some sort of like it was a calculator. Hashing algorithms. Piano wire memory. It was a calculator, but this calculator it had a piece of piano wire, and it used what was it? It used like acoustic. Yeah. I'll post this in here. But it used like acoustic waves. Like it had a little like thing, like a little like transducer that vibrated a piano wire, and that put bits onto this piano wire as it propagated through there at the speed of sound, kind of spiraling in, and that allowed the calculator to sort of like basically push to that and then do some calculation and then like listen for the vibrations on the input, and then that kind of like yeah, allowed like served as like a volatile memory stack, and you had like 100 milliseconds to read it, or else it would whatever get rid of it. But I think this is it. Astonishing old calculator. Oh, yeah. This is the piano wire. So this big coil here, that's where it stores all the memory. So that's 2 minutes and 14 seconds. I'll put that in the chat. And the SWK, the chip. So the actual microcontroller here, I'll post a link to that as well. So it's the CY 8C something 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 something. This chip here. So that's the microcontroller, and I think the FRAM, if you're interested in that, is an FM24W256. All right. Packaging options. I'll open the data sheet for this thing. Let's see if we can find something insightful in here. Let's see. Something that I noticed. I was looking around at like if this could work on Linux, and from what I could see, oh, that's good. Hardware design considerations, GPIO pins, circuit board layout. Yeah, from what I can tell, you require if you're using the PSOC. So all of the PSOC line stuff from Cypress, it has it's a programmable system on a chip. So it's essentially like you can have basically software-defined hardware peripherals, and it's sort of like a little bit of almost FPGA fabric, kind of inside of their parts, and that's sort of their secret sauce, or that's their I guess market advantage. But the problem is all of the tools that generate the bit streams that configure the PSOC, one, are super proprietary, and two, are Windows only. And some people on the internet, some of the I don't know, like sales and marketing people, they're like, oh, if you want to use the PSOC on Linux, you have to use a Windows dev machine, or potentially a Windows virtual machine, and generate kind of like the starter code, which is it's like a little binary blob that you would like link in to your whatever piece of code that you wrote, and from then, once you had that little binary blob, then you could develop on Linux and use GCC and do all that kind of stuff. I am not sure if this will run in Wine. So when using Wine stuff, like, so the IDE, it's probably something based on Eclipse. That's what everybody likes to use these days. Eclipse or JetBrains or something like that. But as far as getting the IDE to talk to a USB device, I've never had any luck, or any good luck with Wine programs doing that. I'm not really, I don't have a lot of confidence in Wine being able to talk to the programmer, but it's worth a try. So it's their PSOC Creator is a free Windows-based IDE. It enables concurrent hardware and firmware design. Great. Well, let's go ahead and install it then. Why don't we? Alright, download PSOC Creator. And they're going to make me sign in. Blah, blah, blah. Alright. Well, you guys, avert your eyes while I type my password in. And yes. Come on. There you go. Okay. So that's all that there. Signing in with my work email. So, all right, we'll save this guy, and then we'll see if it runs in Wine. is still going. Yikes. Big old chunker of a file. What was it? 540 megabytes. Oof. How do I... I always forget. How do you make ls do... dash R? How do you do it based on time instead of alphabetical? Almost all author. Sort by date. How do you do that? Ah, yeah, dash T, dash TR. Alright, so then that's this guy. Okay, cool. Ooh, what is it? Dash LRT? Yeah, cool. Thanks, Bob. Alright, waiting for this to download. It's like waiting for paint to dry. Alright, let's see if this does anything interesting. Yeah, I guess people still do. What was it that installed something on Wine recently that required Adobe Air? I forget what it was. Ended up just abandoning it because it didn't install properly. But yeah, some sort of management thing. Yeah, I think it was like some sort of like IPMI tool for like Supermicro, and god damn it, can't launch browser. Why do you need to launch the browser? To continue, install the missing prerequisites. I need Microsoft VC++ 2013 redistributable or later. Can't launch browser. God damn it. Okay. I feel like there should be like what is it? It's like wine tricks or something like that. You should some relatively easy switch or some like relatively easy option to install this thing. And The Sims 4, it needs this thing. You know, it's just be able to download it from Microsoft directly. But we'll see what the wine forums have to say. I don't know. update for Visual C++, redistributable package. All right, whatever. We'll just get that to go. Recently found out a QA stats tracking program. I'm guessing I wrote an MS Access back in the 90s is still being used. Oh man. Yeah. I don't know. It's I keep discovering like just how much of the world is held together with like I don't know the software equivalent of like bubblegum and duct tape. It's just like how does the modern infrastructure of planet Earth even like prop itself up? You know, it's like stuff like that. You know, but that's pretty funny. Microsoft Access. Yeah, we're using Altium here at Ologic, and they have a like a database library, and they support two types of databases. You can either have a database that uses Excel spreadsheets as tables, or it can have a Microsoft Access backend. I don't even think they have like SQL databases, but you know, that's how the world works, I guess. You know, use what you can. Put both of these. Use what you can, you know. So I will download both of these VC++ redistributables, and okay. So downloading the 64-bit and the 32-bit one. I guess we'll see if try the 64-bit first. What was it? VC redist. So wine VC redist x64. See if we can do something with that. I agree to the license terms and the conditions. Cool. So that worked, and now let's try PSOC creator setup again. Let me see if I can get some music playing in the background here. Okay, can't launch browser, that's fine. It says it's not recognizing that. So that means I probably need the x86 one. prerequisites. Oh, nice. Okay, so that worked. Let's do a custom installation, I guess. Figure out what we need. Creator 4.2. Install all the mandatory things. GNU CS. Ooh, 8051 debugger. That's kind of cool. Reference component catalog. Yeah, whatever. That's fine. History when it works, so I can see the wine command list. All right. So really, the issue with this one is it didn't have the C++ like redistributable or whatever. So open this up. Burp. Yeah, so all it was is I had to install, it's the x86 version of what is it, Visual Studio C++ redistributable thing. So this was the one thing that I had to do to make it work. Put that there. And just to kind of save you some Googling, I'll post a link. So I don't know what it's doing right now. Downloading a bunch of useless garbage, filling my computer with it. Ugh. So that there, that's the download link to get the Visual C++ redistributable package. And then I guess Wine doesn't work with like 64-bit systems, or doesn't show up. I get the API that Wine implements is x86 and not x64, I guess. So installing the 64-bit installing the 64-bit redistributable package didn't actually do anything. It was still not recognized by the installer and all that kind of stuff. So. Still making progress here. That's good. Almost done. Woo! Is it finished? Oh, no, now it's thinking. Contact information. Required field, huh? My name is Swedish Hat. And that is, well, my name is ASDF. Let's do that. Required. Why do you have to put in your email address to open their ID? That's stupid. Oh, continue without contact information. The heck? administrator and the update manager and no contact info. Cool. Whoop. The monitor just fell down. So I'm getting a warning message on my screen. What does it say? Encoder overloading. Consider turning down video settings or using a faster encoding preset. Oh, cool. Hey, cool. Check out this error message. It says nothing. Show details. Oh, more nothing. That's cool. Again, a whole bunch of useless nothings. Checking for updates. I don't want to do anything there. Great, no updates. So I guess I can exit that. Wow, okay, cool. We got the IDE installed, that's pretty exciting. So I am happy about that. Let me then, spam you just for downloading our software. Start a new project here. God, this is so small. Why is this? Wait a second. New file. I want to create a new project. Can you not create new projects in this IDE? What the heck, man? PSOC has encountered a problem and must close. The problem it encountered is that I closed it. Why are you like this? CD line drive C program files x86 Cypress. I love seeing whenever I run Wine, it always has these like, you know, for what it is, like Wine is an amazing project, and like I'm so impressed that it can do what it does. But it's like it's funny seeing these things where it's like, oh yeah, this thing we know this is wrong. It's like warning, fix me, you know, unknown element, dude. It's sort of like we're getting by as best we can here, but no promises. Yeah, I don't know. It's cool that it installed, but I have my doubts that we'll be able to do anything useful with this. Awesome. I love it when it just crashes like that. Why Linux on the desktop? Every time I try that, I end up back on OS X or Windows 10 because of business app support. Um, you know, the reason I have Linux on the desktop is because I'm a glutton for punishment, and I don't know. uh, I mean, most of the stuff that I do is like, so I have a separate laptop for work, and that work laptop is Windows and dual booted with Ubuntu on it and stuff. But I mean, for the kind of things that I do for my personal laptop, I can get by with all sorts of with only Linux stuff. And I don't know, it's just kind of a lifestyle choice, I guess. Um, yeah, masochism. Yeah. So whatever. It's got its issues, got its quirks. Um, I don't know, but it does other stuff really well too. Um, but yeah, just trying to bridge that gap between Windows stuff and Linux stuff has always been the bane of my existence. So I think okay. I think it's about that time of the night where I think I'm probably gonna sign off. Um, and uh, see if I can boot up a Windows machine and try this then. Oh yeah, dude, SSH shells. Yeah, it's like, and what I found is like, I don't know, dealing with SSH in Linux is much more like, I don't know, it's a much happier experience than trying to, like, I don't know, use PuTTY or use I don't know what, hyperterminal. I don't know. I normally use PuTTY for my SSH stuff on Windows anyway, but yeah, I don't know. It's like I try not to be too big of a fanboy about it, because I understand like how much Linux makes my life difficult in certain times. But you know, it's I prefer freedom and inconvenience more so than, like, I don't know, the Windows man or the Mac OS man telling me how to live my life and run my software. So I don't know. It was also kind of cool. PuTTY plus screen bounce plus inner screen. Cool. Nice. Yeah. So, all right. I think what I am gonna do though is I'm gonna shut down for now, and then the next stream is gonna be probably done on a Windows machine, and then I'm gonna do some just blinky LED type stuff. Rage because the meta key is not Control A. Yeah. So I think that's pretty good progress for now. Just kind of bummed couldn't get it to blink tonight. But in any case, I suppose I'll see you all next time, potentially. But anyway, yeah, thanks for watching, guys, and hope you all have a good rest of your night. And until next time.